This is Jonathan Van de Zand, the Director of Computational Chemistry here at Rowan. Today I will be providing a quick overview of how to run an optimization and frequencies with the Rowan platform. First, log into labs.rowansci.com and click on New Calculation. Here we can upload a file, input the smiles of the molecule, or draw a 3D structure. We can select the periodic table and the carbon atom to add a carbon, and select the hydrogen here to add another carbon to produce an ethane. We can decorate this ethane with various different atoms, such as a nitrogen on this side and a chlorine on the other. We can quickly optimize this with either a force field or with GFNFF to produce a better starting structure for future optimizations. Let's go ahead and save this molecule and change the name to its smiles name. We can select the level of theory, here defaulting to AIMnet2, which is excellent for organic molecules. Then select the tasks of optimize and frequencies and click Submit Calculation. AIMnet2 is a very quick neural network potential and can optimize molecules like this in only a few seconds. If we click on the Optimize tab, we can see it is already completed and has done 53 steps in the optimization. We can see it changed slightly from our starting geometry to a slightly more accurate geometry. We can then visualize the frequencies, with the lowest frequency here being a WAG, the chlorine stretch coming in at 777 wave numbers, and the highest frequency being an antisymmetric hydrogen stretch on the nitrogen. We can also compare this to the gauche version of this molecule by clicking on the Resubmit button, Resubmit as Calculation, and editing the molecule. If we select Edit, Bond, Angle, or Dihedral and select the atoms of interest, we can then rotate around this dihedral to produce the new structure. We can clean it up with a quick GFNFF optimization and go ahead and save and rename the structure. We can then select the optimize and frequency tasks and submit the calculation. While we're at it, let's rename our initial molecule to have trans appended to it so we can differentiate. The optimization of the ghost structure is now done, and we can see that it was able to optimize in only 36 steps, and that all the frequencies are positive. We can select both of these to compare their energetics, and we find that the trans structure is 0.6 kcals per mole higher in energy than the ghost structure. We can also overlay these structures to see how they differ.